the structure of the atom. We're going to look. A nice way to introduce is to look at the neon light, and that neon light emits certain frequencies. I don't know whether neon's there. I don't think it is actually. Neon looks something like this. It actually emits quite a lot of frequencies, I believe. Anybody see neon on that spectrum chart up there? Oh, my eyes. Oh, neon's at about this level here, if my eyes serve me correctly. The spectrum chart to the right. So neon actually has lots of visible wavelength lines that are emitted. And so what we call this here, firstly, just to get through some terminology, this is a line emission spectrum. Does anybody know what this one's called up here at the top? Absorption spectrum, yeah, absorption. I was absorption spectrum. You might, if you guys aren't carrying coloured pencils, are you? Right. Oh yeah, that's a nice picture. Yeah. Oh yeah, that's a great picture. Is that in 16 by 9? Yeah. We might be able to put it on our Moodle site. You can send it to me. Charge fees, yeah. Okay, so the line emission spectrum, essentially these are for neon, and I don't, oh, this might be neon here, I'm not sure. Neon looks something like this. There are lots of wavelengths emitted in neon. Each of these wavelengths, or it's a small area of wavelengths, okay, corresponds to an energy level jump in the atom. Okay, and I'll bring up an energy level diagram in a second because we won't talk in these spectra so much. We'll talk in energy jumps. And so what I might do to get a line emission spectrum is actually I'll say I can excite the atom and cause the electrons in that atom to lose energy in the form of a photon. Now, I'll just be careful with using photon here, a packet of energy. Because we're talking a little bit about the wave properties of the energy that's being emitted. So, what does it mean to excite, do you think? When I say, how do I have an atom in my hand, how do I excite it? Add energy to it. Physically, what can I do? I could rub my hands together. I could jump on it. Okay, that's going to create heat. I could fire electrons at it. Yes, with an electron gun if I had one of those. I could heat it up, and heating it up is just firing light at it. Okay, so this can mean many different things. Light, heat. These two are the same things. Essentially, what I do is add light to it in most cases. Electrons. Okay, that's how I excite that atom. What about the absorption spectrum? How do I create a spectrum that looks something like this. Pass it through a prism, yeah, okay. So if I take a triangular prism outside of some sort, and you've done this, it wouldn't work today. Some sort of a prism, okay. Everybody's seen one of these things, usually made of glass. Doesn't matter, they can be made of plastic as well. And I shine light through that, then the well, actually sunlight, which is white light essentially. And so white light is made up of all of the colors of the rainbow. I'll draw some colors of the rainbow coming in. We see this as white light, and I haven't necessarily got these in order, sorry. Roy G. Biv, red, orange, yellow, green. Well, I did. I kind of put them in order. That was just a fluke. This is white light. This is white light coming into that prism, and then it's refracting through that prism, and these refract at different rates, or they travel through that glass at different speeds, and it breaks it up. And this is a bit misleading, so I'll just say that is white light overall. That's not a very good. I'll make this bigger and say that is white light going in. Okay, and what comes out, of course, is all of the colours of the rainbow, because they travel through at different speeds. There's refraction that occurs, so they don't travel through it in a straight line. Actually, I better put some orange in there. And we see the white light, that is the sunlight, broken up into its constituent colours. And that, if we see all of those colours at once with the spectroscope, and a spectroscope is just a tube with a prism inside it, with a screen, okay? And if we see all of those through a spectroscope, then we see this whole spectrum. But this is, with the lines in it, it's called an absorption spectrum. Without the black lines in it, it's just the continuous spectrum of all the colours of the rainbow that we can perceive anyway. Being that this is an absorption spectrum, what has happened? Why are these black lines here, do you think? What mechanically have I done to that light to make the black lines appear? Something had to absorb those frequencies, didn't it? And so I could do that. I could do that by placing a gas in the way. So imagine I have the white light coming into the prism and it refracting out into its constituent colors. If I put something in the way here, and that might be, say, and I don't know what, it doesn't have a corresponding, we'll talk about that later, but if I put a gas in here, in between the white light and the prism, all of a sudden, what happens is that gas takes on that energy, takes on all of the colors, or some of the very specific colors of the white light, and it absorbs them. You know very quickly, though, it emits them again. Why are these lines showing up then? If this gas is going to absorb the white light and then re-emit it, why don't we just see a continuous spectrum? Exactly, yeah. We have a scattering effect occurs. Doesn't necessarily, yeah, that's good. Doesn't necessarily re-emit in the same direction. So we might have this gas here. Actually, I'll describe this later in more detail. But essentially, what's going on is that red light, or much of that red light, might be scattered off in the other direction by this gas. And so, still, some of it's going to be scattered in the correct direction towards your eye. But you're going to find that to us, it appears in all of this brightness here. To us, that appears as a dark spot, even though there is some light there, okay? Let's have a look at, now more importantly, energy levels. This is an energy, we might just go straight to hydrogen, actually, because we spend a little bit of time on this. I'm now going to relate what we've just spoken about to this diagram here. Now, this is an energy level diagram for atomic hydrogen. Atomic hydrogen. I know that because of this value here, and because it says in the book. But I recognise this value here, and I also recognise these numbers because I've been teaching it for a while. These numbers look very familiar to me. They're not the same for every atom. They're very, what we call discrete, very different for every atom. Okay. Now, imagine that gas that I put in the way of the prism between the white light and the prism was hydrogen. Let's now have a look at this atomic hydrogen. I'm going to make this diagram a little bit smaller first so I can draw on it and draw next to it. I hope that's still clear. As that white light comes in, let's send some white light into this atom. Now, I know that this is not your typical idea of an atom. It might be related to this diagram, which is not really right. Okay, we have electrons in energy levels. These outer levels here correspond to these higher energy states here. The inner levels correspond to this ground state energy here. You'll notice that the numbers, the values are minus, in the minus values, kind of minus energy. They're written that way because they are bound. These energy states are electron energy levels, and they are bound to the atom, and so they say they are negative. In order to make a ground state electron, or an atom, this is one single atom, in its ground state, to allow an electron to go free, I have to give it 13.6 eV of energy. And then that electron will raise up here and go into the continuum, which is a free electron, really. Okay, so we're looking at the free electron moment up there. Actually, I'm going to remove this anyway because that's not right, so I better... Okay. Free electron. Now, you notice this is called the ground state. First excited state, second excited state, third excited state. There are other excited states in there, but they're not listing them all. If I send, let's send our sunlight into this atom. Now, this diagram is not correct either. This is just an idea about what's happening. Imagine this is our hydrogen atom. I'm sending white light in. White light is all of the colours of the rainbow, of course. Yellow, green, blue, and violet. I'll just stop there, that's enough. If some of this light, this is a continuous spectrum, remember, so there's innumerable, it's the whole region of the visible spectrum coming in, and infrared and ultraviolet, and maybe some other regions of the electromagnetic spectrum. But we're only going to look at the visible light spectrum, that small portion of the electromagnetic spectrum. Some of that corresponds very specifically. Now, let me show you. Energy is equal to Planck's constant multiplied by the frequency. Now, what that says is the frequency of these wavelengths, the frequency of this electromagnetic radiation has an energy associated with it. Now, if I have this frequency in hertz, Planck's constant in joule seconds, then I get an energy in joules, and we're talking in EV here. Okay, so but that doesn't matter so much. Just know that the frequency is proportional to the energy, or the energy is proportional to the frequency of light. Now, which one has the highest frequency here? Is it going down the page or going up the page? Higher frequencies as we go into the red? Going down, yeah, that's right. Okay, so frequency is increasing down here. So that means that blue has the highest or the lowest energy? Highest energy, doesn't it? Out of all of those colors there. Imagine blue corresponds to an energy jump in this atom. And I'll do an energy jump that's probably possible for the blue. Corresponds very specifically to that jump for that atom. This here is too big a jump, incidentally. This jump here has to be a UV ray photon. And I can't draw a UV ray photon, not in the format that I'm drawing here. Okay, let's say that's a UV ray photon coming in. Now, that's UV. Now, UV could cause this energy jump if it has this very specific energy. I want you to know that the photon will be accepted by the electron only if it corresponds exactly to one of these energy jumps. That's how we see it. Okay? You can't have a photon come in and make it jump up to some impossible energy state. It just doesn't happen. Right? That's the way we see it. So this red light might correspond to this energy jump here. Okay, so I'll say this is because of the red light. Actually, no, I'll say it's because of the blue light. Say it's because of blue. Now, blue comes in, causes that jump. The electron gets excited. The atom itself gets excited. What it doesn't like to do is stay excited. It likes to go back to its ground state very quickly. And what can happen is you can have this energy jump very quickly back down. What then happens? It emits what? It emits that blue frequency there corresponds to this energy jump here. That energy jump here corresponds very specifically to that blue frequency again. Okay? The atom emits a blue photon. It's not necessarily in a straight line, as we said. There's some scattering that may occur, or that will occur. Some of these smaller energy jumps up here might correspond to a red region jump. So I know the diagram's getting small. There's a jump there. The arrow is going to be the size of there. That could be a red photon. Comes in, causes that jump. The atom's not going to like being in that excited state, so it will very quickly jump back down and emit that same photon. What I'm talking about is the difference between these energy levels, not the fact that as we go higher, yes, the atom is increasing with energy as we move up this, but I'm talking about the difference between these two energy levels only. And this is a big difference here, you can see, about 10 eV. These differences here are much smaller, 1 point something, okay? Much smaller. And so for these small jumps here, the coloured or the visible region of the spectrum has enough energy to make those jumps. Okay? So I could send light in, and sending light in is like heating up this atom, isn't it? I might, yeah. Well, it's essentially, imagine I've put a flame under this atom. This very specific atom. Here's my flame. That's my idea of what a flame looks like. Okay. I've added heat to this atom, which is light. It causes that atom to get excited and emit its own light. These energy jumps are very specific. Very specific. And so if I heat up an atom and I'm not sure what it is, and it emits a spectrum that looks something like one of these, what can I say about that gas that I can't see? What's that? What can I say about this if I didn't know that this was hydrogen and I heated it up and I noticed and I looked at it through a spectroscope and I noticed that it showed these lines here. Now that's the hydrogen spectrum as in colours. There's a couple of violets there that you probably can't see very well on this board. These correspond to energy jumps, energy levels in atomic hydrogen very specifically. This is the signature for hydrogen. Okay? Hydrogen is going to make those energy jumps. Let's write down some information because I've talked a lot. Line emissions, spectra. Spectra is the plural of spectrum, are the result of electrons transitioning from excited states to lower than excited states. So I'm not saying which states. I'm just saying that anywhere up here down to lower energy states, we will see emission spectra. And we will see them very specifically in this case for hydrogen. And it will look like this for hydrogen, this spectrum here, this line emission spectrum. Absorption spectra are the result of electrons transitioning, and we call these transitions. Any of these, up or down, is a transition. From some lower state line emissions and absorptions. Are a signature for individual elements or compounds. So this is very useful very useful in spectral analysis. Where were the, or have I talked about the noble gases and something interesting about their discovery in the past? What is it? Helium was discovered in the sun, so, but we haven't been to the sun, so how's that possible? Yeah, but the absorption spectra, that's right. Exactly. So John has said that they found spectral lines. So they looked at the sun through a spectroscope and probably some filters, I imagine. and and they saw some lines, that were missing that didn't correspond to any of the known line emission spectra that they already knew. They had excited many different gases. They'd looked at their spectra and said, well, hang on, what's this black line here? Because that I don't even know what that is. And there's another line here that doesn't correspond to any of our known spectra. What is it? What will we call it? What will we call this unknown gas? Why helium? Yeah, because helios is the Greek for the sun. Okay, so helium is of the sun, discovered on the sun very late, I think late 1800s. Many of the noble gases were not discovered until very late because they don't like to. It's not that they don't react; they can react, but they don't often react with normal chemical reactions under normal circumstances. And so we just didn't know that they were there. We found them when we discovered the spectroscope. Okay, so let's have a look at that. I'll draw the sun. That's the sun. The sun's really orange, really, isn't it? Okay. That's the sun. Sun. In case that wasn't clear. Now, what does the sun burn and create? Yeah, that's right. Respectively, it burns hydrogen and makes helium. Uh, it takes single protons, squeezes them and heats them up, and joins them together, fuses them together to make helium, because helium is two protons, isn't it? So what happens is the sun's atmosphere has a lot of helium in it, of course, and so this would be helium gas, and somebody on Earth looked at the sun through a spectroscope. Yeah, people have been known to do that in the past. Not so sharp. Now, through a spectroscope, and they saw this. Let's find the actual spectra. Uh, helium absorption. Oh, did I not? That's right. Is it frozen? It looks like it's frozen or something. Here we go. I think this is it. I can't see close enough to know that is actually helium. We'll just oh, okay. Hydrogen. These are hydrogen lines, obviously. This is a helium line. So what they noticed was, what this person was seeing, please, was this. And they said, oh, there's hydrogen. Yeah, I can see hydrogen missing there. What's this stuff here? What's going on here? Yeah, and that's when they decided that there was this gas around the sun that was absorbing some of the sun's white light, and that they would call it helium. Helium was discovered on the sun. Now, that doesn't mean that helium is orange. Okay. Well, no, what you could say is instead of saying that helium is orange, which is uh, just not true, you could say you could say something else, Matthew. What would you say? Yes, that's good. Helium, the gas, happens to absorb very specific frequencies, which we call orange. Yes, that's good. Yeah. Yeah. Okay. So helium tends to absorb the frequencies in the continuous spectrum that correspond to what we would call the orange color, and that's kind of helium's signature. Okay. Why does it do that? It's because as this white light came in. Oh, sorry, hang on, that's not right. We're not quite getting white light. As the white light came out of the sun, it was there was everything else was there afterward. The green was there, the red was there, the yellow was there. Oops, more red was there, yellow was there, blue was there, orange was or a very specific uh, wavelength of orange was missing because the helium had absorbed it and caused a lot of it to scatter. Okay. I hope that's clear. Uh, Helium. Yep. Okay. Now, so I better say more about. Oh no, that's okay. I think that's a sufficient uh, description. One more thing before I go to an applet which will show you discharge tubes, which was the neon lamp that we were looking at the back there. This here, a student asked me recently why these very specific energy states. This is a tough question. Now, at high school, we tend to just say, well, there's very specific energy states around the atom. Electrons can only exist in certain places, and that's where we stop. There's no explanation, or there's often very little explanation about why is it minus 3.4 EV? Why is it minus 13.6 EV that exists? Yes, that's right, and that's the description that I made for a long time. I said, well, those are the energy levels that are available for the electrons that orbit around that atom. The Schrodinger equation. Yes, very good. And say what? Yeah, exactly. In layman's terms, okay, so Schrodinger came up with this idea with his equation, and I haven't written his equation for a while. Don't ask me to remember it. It goes this long. Okay, now Schrodinger equation essentially says electrons can exist in certain spaces around, or you're likely to find an electron in this place. And why? What do we know about electrons? We often say that they travel with kinetic energy equal to half mv squared, and because classical mechanics says this, they also travel as a wave. Okay. Now let's draw a simple hydrogen atom with a proton in the center and a single electron. This idea that we've had for all of high school that says that hydrogen is this thing, and the electron travels as a wave around the atom. Okay? Travels as a wave around that atom. Now, why is this here, this position, energy-wise, this energy position from the nucleus, this binding energy here, very specific? Proton has a very specific charge. We know that it has 1.6 by 10 to the minus 19 coulombs. So does the electron. They have equal and opposite charge. What about why I can shine light on this atom here, and it can go to higher energy states. What's going on there? Yes? Yeah, okay. So by increasing its energy, we increase its speed. By increasing its speed, it essentially it can do this orbit faster. Okay. Now, have a look at this diagram. This is from a Year 11 textbook because it's better than I can draw. We might have to go to old school. You might remember this text. You might remember this diagram. Here it is. Now, does somebody want to say something about, before John does, about what this diagram describes? Whoops. Hang on, I didn't copy it properly. Hey, make an attempt. I'll try not to pick on you. Yeah, I'll make it smaller in a second. What is this showing? This is this isn't psychology. No, it's not showing a star and a butterfly. It's okay. It's here we have a nucleus and we have an orbiting electron, and that orbiting electron is moving as a wave. This is a very simplistic diagram, of course. This one here, it's the same atom, but it's exactly the same nucleus in the center, but something's going on with this wave pattern that's formed by this electron on the right-hand side in B. Okay, John, you got an idea? Is a standing wave, isn't it? It's forming a standing wave. This wave is arriving in phase, isn't it? It's possible at that speed, whatever kinetic energy that electron has, this position around this nucleus is possible. The wave function doesn't collapse. Okay? What's happening here in this diagram? Yeah, that's right. So in this diagram here, it's exactly right. It's exactly the same atom in both cases, we'll say, except this electron has a different energy. Therefore, it has a different frequency by E equals HF, and at this frequency, its wave function collapses down on itself. There's kind of a destructive interference that is occurring here. The wave function collapses. This is not an energy level that is possible. Okay? And this is how Schrödinger described it. He did it with some mathematics too, which was very good. But that's beyond the scope of this course. I'll make this a bit smaller. And we'll say here a electron frequency is such that the wave function is possible, arrives in phase, or forms a standing wave, and in B, the electron frequency is such that the wave function collapses. This energy state is not possible. This energy state is. And this was Erwin Schrödinger in the 1930s, I believe, came up with this. 29, was it? 1929. Thank you, John. What was it? Oh, yeah. No, that could be about right. SCHRO with the two little, I can't remember what they're called, above. DINGER, Schrödinger. Sorry I talked all lesson, folks. It's